Okay, with this video, we're going to derive the Michaelis-Menten equation. And you're not expected to know how to do this for the midterm exam, for example. But so it's just purely for fun, or just to show that we can, with rational thought and logic, come up with this equation. We're going to start with the molecular picture. Enzyme and substrate first bind with each other. That's governed by these association rate constant and dissociation rate constant K1 and K minus 1 to form the enzyme substrate complex. Then in a second step, we get chemistry governed by Kcat to regenerate enzyme and product. Now, if we knew the enzyme substrate complex concentration, we could very easily write the rate, velocity, is equal to Kcat times the concentration of ES. And now what remains is to derive some expression for the amount of enzyme substrate complex in terms of parameters and things that we have control over, such as the total enzyme concentration, which can either be in its free form or in the form of the enzyme substrate complex. And the substrate total concentration, we also have control over that, and that's also in its free form or the enzyme substrate complex. What we're going to start with is the Haldane's steady state assumption. Which says that the rate of formation of ES is the same as or approximately equal to the rate of its destruction. So the rate of destruction of ES is governed by K minus 1 dissociation or chemistry Kcat. So those are the two ways, the two processes by which we can get rid of the enzyme substrate complex. And that's going to be equal to the rate of formation. It's governed by K1 E in the free form, S in the free form. And at this point, we're going to divide both sides of the equation by K1, the association rate constant. And that's just to get all of the kinetic constants on the left-hand side. This combination has a special name. It's called the Michaelis-Menten constant, which means we can rewrite this as ES times Km is equal to E in the free form times S in the free form. Now we're going to make another assumption, and that is that the enzyme is of much lower concentration than the total concentration of substrate. And under this condition, where enzyme is limiting, then the total concentration of substrate is approximately equal to the free concentration. We can kind of ignore this term because there's so much substrate. So we'll make this substitution that the free concentration of substrate is, we can replace that with the total concentration of substrate. For the free enzyme concentration, we have to do that more completely, and we rearrange this equation into free enzyme is equal to the total enzyme minus the enzyme substrate complex. For enzyme, it's quite possible that a large majority of the enzyme is saturated with substrate, so we have to write this out more completely. So now with these substitutions, we have ES times Km is equal to E total minus ES times S in the free form, which is the same as the S and the total S. And now we're going to distribute and write E total S total minus ES ST. I'm going to collect terms in ES by adding ES times substrate total on both sides of the equation, so that we can write ES times Km plus S total is equal to E total S total. And then I divide by Km plus S total, both both sides of the equation to get rid of this term, so that we have enzyme substrate complex is equal to total enzyme times total substrate divided by Km plus total substrate in the system. And now the only thing left to do is to substitute into our original equation to write V is equal to K cat enzyme total substrate total divided by Km plus substrate total. And that is exactly what we're looking for, the Michaelis-Menten equation.